Okay, we're going to start talking about concepts of circles. Now, first, before we start off circles, we need to know the definitions of concepts that are in circles. So, to start off with, in circles we have three definitions that we're going to mainly focus on. The first one's chord, second secant, and tangent. Now, a chord is a segment whose endpoints are points on a circle. So, for example, I have two circles here. If I have this circle, here's an endpoint that lies on the circumference, and let's put another point over here. The endpoint must always lie on the circumference. So we can call this point A, and we can call this point B. All I have to do is connect it to make it a segment. This is a type of chord. So another way of thinking about chords is, for example, harps. When you have a harp, you have strings, and these strings are attached from one end to the other. It doesn't go any further, and it doesn't stop midway. If it would fall flat on the ground, so it wouldn't be able to work. So let's give another example. It can be horizontal, but it can also be a vertical line. So I have 1 point, 2 points, connect them, and I can call them whatever I want, A, B, C, D, or in this case, X, Y. Both of these are examples of chords. Following is the concept of a secant. Now, a secant is a line that intersects a circle in 2 points. Now, this is important. It's 2. But now let's also take a backtrack. It is a line. So a line, as we know, goes infinitesimally in both directions. So if I draw a line straight through it, I have 2 points that it crosses over. I can call them any value I'd like. So I can call them A or B. Now let's try another one. Just draw a line. Doesn't matter how it is oriented. Can be vertical, horizontal, still doesn't matter. Can call them the points whatever I'd like. In this case, we'll just call them X and Y. Now, you notice in the first and second one, I've been calling them A, B, and X and Y. Reason being, those are the most common variables that people use. Now, tangent. A tangent is a line in the plane. Now, yet again, a line in the plane of a circle that intersects the circle in exactly 1 point. No, not 2, not 3, 1. Now, this means that it can't stop in the middle of the circle and then continue on in one direction. So, for example, that intersects the circle at 1 point. However, it is not a tangent line because it is not a complete line. It must be keep going in both directions all the time. So let's take that out. So an example would be this one. Draw my arrows to show that it will continue on, and this point touches. So basically touching at 1 point or intersecting at 1 point is an example. So I can show you another one. X, and let's call this point A. So both of these lines are tangent to the circle. They touch at one singular point, and they are still aligned, so they go on forever. Now, underneath there are a few example problems. Please try to do those problems on your own. Alright, you might want to pause the video now in order to try them. Next concept is the idea of tangent segments. So we discussed what a tangent line is to a circle. Now we want to go a little bit further and talk about a tangent segment. Now a tangent segment is a segment that touches a circle at one of the segment's endpoints and lies in the line that is tangent to the circle at that point. Now that sounds all really confusing. So let's condense that to something a little easier. The tangent segment is basically a segment that is perpendicular to the radius formed with its endpoints at the point of tangency. So here, I have a radius and a tangent line that intersects, connects at the point of tangency. At this point, I have my right angle. Now, given a right angle, I can now connect my center of a circle to the tangent line, and if we do that, we're able to create something known as a right triangle. So below, we are able to see that we have a complete circle. if I connected the one line, so let's make it blue, I'm actually able to form a triangle. So we have my base, my height, as well as my hypotenuse. Now, with triangles, we're able to recall information and solve for information. Equations that we can use would be the trig rules, sine, cosine, tangent, but we can also use something known as Pythagorean theorem. If you recall, the Pythagorean theorem is a squared plus b squared is equal to c squared. C is always by itself. Now, when c is by itself, it has to be the longest side. So we're going to denote the hypotenuse as c. It's always, always, always the hypotenuse. Now, the other two sides, the legs, can be interchangeable. So it can be a and b or b and a. Doesn't matter how you add them and square them. Doesn't matter whatsoever. Now, let's try a practice problem with this. All right, I'm giving you guys a figure where the radius is 12. The line from the center of the circle to the tangent is 13. And then I need to know the side length from the point of tangency to where the line intersects the tangent. So this might be a little confusing. What you might need to do is translate it to an actual right triangle. So I have the blue mark to help you realize that that's the hypotenuse. So we're going to call that 13. We're going to call the one leg 12 and the other one x. If we recall, a squared plus b squared equals c squared. And c is always the hypotenuse. Now, I'm just going to call this b and this a for the time being, because I think in the other section I call it the other way around. So just plug the values in. 12 squared plus x squared is equal to 13 squared. Solve out. 144 plus x squared is equal to 169. So all I had to do was just square out my value. So 12 squared is 12 times 12, or 144. 13 squared is 13 times 13, giving me 169. I need to get my x value by itself. So first, need to subtract both sides by 144. X squared is equal to 25. Now, how exactly will I get rid of the squared value? So there's an operation that looks very similar to a check mark. It's known as the square root. If I square root both sides, it reduces x squared to x and reduces 25 to 5. So x is equal to 5 in this case. There are two more problems below, so you might want to pause the video and attempt them on your own. Now, next we need to look at concepts of arcs. Now, on a circle, there are an infinite number of points. The distance between any two given points is known as an arc. No, not like a boat. We write arc with a semicircle over the 2 points. So for example, I can say points from A to B and have an arc over top of it. So it would be known as arc AB over the 2. However, there are 2 different directions. So how are you able to determine what the arc is? So in this case, in the figure below, we see AB. So is AB blue or green? Is it going the shorter distance or is it the longer distance? Actually, it's both. It can be either of them. Now, to be more specific, there are 2 types of arcs. There's something known as a major as well as a minor arc. So, the longer arc formed is known as the major arc, while as the shorter arc formed is the minor arc. So, looking back at the previous picture, in this case, we have green and blue. We definitely can see that blue is a lot shorter than the green one. So blue would be the minor, and green would be the major. So as I said, so the major arc would be green, and the minor would be blue. Now, next concept we're going to talk about is the arc length. Now, the arc length is a portion of the circumference of a circle. So we'll be writing the portion of the circumference of the circle in terms of the total degrees in a circle. So in a circle, we have a total of 360 degrees. Now, if I stand in the center of a circle and I spin around, that will be 360 degrees. Now, if I was on the outside of a circle and I walked around it, it would actually be 360 degrees as well. It doesn't matter whether I'm starting in the center or if I'm walking around it. If I go in a complete circular rotation, it will be 360 degrees. So because they're actually exactly the same, maybe I'm getting a little ahead of myself, at the center of the circle, we're able to spin 360 degrees. So the ratio from the circumference to the center is actually 1 to 1. In other words, when it's 1 to 1, they're the same. They are, in fact, equal. So if I have the center and I turn 110 degrees, what exactly is the distance I travel? Well, it's a 1 to 1 ratio. It's exactly the same. They're equal. So it's 110 as well. There are 3 problems below that I would like for you to try as well. If you need to, you can pause the video and keep working. Next one. An inscribed angle is an angle whose vertex is on a circle and whose sides contain chords of the circle. At the side of a circle, we're able to see 180 degrees. So the ratio for circumference of the circle is 1 to 2. Now, before I fill in the next section, it sounds already really confusing. So I have a little person right here. This little person has a viewpoint of 180 degrees, while the circle is a total of 360 degrees. So whatever we see, we have to double it in order to get the circle's full degrees. So in other words, the arc is double the inscribed angle, or the inscribed angle being our viewpoints. So let's try an example. Let's actually start with the second one. I'm standing right here, and I'm looking out. My viewpoint is 15 degrees. However, considering the whole circle, we said it was 1 to 2, it gets doubled. So the degrees of this arc is actually 30 degrees. Let's take a look back at the first one. Here's my little person. I am looking and I see 170 degrees. So 170 out of 360. That's a lot. Now I need to take a step back. So if the circle is double, we have to do the opposite of doubling, which would be halving. So instead, I have to divide by 2. So half of 170 would give me 85 degrees. So note, in the first case, we have to divide. In the second case, we have to multiply, depending on the direction. There were a few problems. You might have wanted to pause the video and try those 3 problems. I'm going to wait a second so you can try those problems. Now the last concept. If 2 chords intersect inside a circle, then the measure of each angle is 1/2 the sum of the measures of the arcs intercepted by the angles and its vertical angle. Yeah, that sounds really confusing. So let's condense that. What I condensed it to is, so twice the vertex is equal to the average of the arcs. So let's go through this one example problem. Well, This is what I'm going to work through with you. So in this case, we have arc 1. So it doesn't matter which one I call arc 1. We're just going to say it's 25 degrees. Arc 2 is 75 degrees. And the middle is 50. Now, in words, I said twice the vertex. So I'm just going to write that equation. Twice the vertex is equal to the average of the arcs. So that would be 75 and 125. Oops. Little mistake. Sorry, that's supposed to be 175. So it would be the average. So add them both together. 25 plus 175 over top of 2. And 2 times the vertex, or 50. So 2 times 50 is equal to 25 plus 175 over top of 2. 100 is equal to 200 over 2, or 100 is equal to 100. So this wasn't exactly an example problem. This one was just to verify how you would do the problem. So given 2 arcs of 25 and 175 and a vertex of 50, we multiply the vertex by 2, and then we find the average of this. In other words, average is, what's the middle? Or what lies exactly in between? Let's try an example problem. So the example problem, I have the 2 arcs, arc 1, we're just going to say is 30, arc 2 is 90. The vertex is x. Put in an equation. 2 times x is equal to 30 plus 90 over top of 2. Cross multiply, so let's put a 1 over top of this. If I cross multiply, I get 30 plus 90 is equal to 4x. Combine, I have 120 is equal to 4x. Divide both sides by 4. X is equal to 30. There are 2 problems following this I would like for you to try, so if you'd like, actually you can just end the video or pause it, whichever you'd like to do. You can go back through any of the previous problems to see if you need refresher, or if you have any questions you may ask later.